Professor Mani, kindly start, please.
Okay, thank you very much. It's a pleasure and a privilege to be invited to such a meeting about Professor A. N. Mitra. I was a student of his. He taught us mathematical methods of physics, and a little later, informally, quantum field theory. He had finished his PhD from Cornell and then come. I had not explicitly written anything for here because I was not absolutely sure of all the details, because I have used my memory, and that's a very long time ago. My memories of him are after Delhi University. I met him in Trieste, and he was looking at the nuclear levels in great detail. I was wondering, who is a mathematical physicist? Why should he spend so much time in working out all the details of nuclear levels? Little later, I realized that he had actually showed the presence of strangeness, which was required to understand the nuclear levels. And I believe he was the first person to show this. It shows the importance of looking at details. Then when I was in IIT Kanpur, I was a candidate for a promotion, and he was in the selection committee. So he did not have any informal exchange. I met him very briefly, and he told me I should continue looking at low energy physics also, which I did to some extent. Now I will proceed with my regular talk, which is on quantum thermodynamics of small systems, the Anyonic Otto engine. This has been done in collaboration with Professor Sridhar and Ramdas. Ramdas was a PhD scholar with Sridhar. Right now, he's a postdoctoral fellow at Math Science. Now I'll go to the next slide. Thermodynamics is an empirical. Shall I proceed? Professor Mitra.
Okay. Please.
All right.
Please.
Thermodynamics is an empirical and phenomenological description of matter at the macroscopic level. We all know that, where the number of particles in the system is of the order of Avogadro number. It was of academic interest to stretch the thermodynamic line of thinking to small systems in order to probe the limits of applicability of concepts like temperature and entropy. This happened because small systems could be prepared, and in the last few decades, several small systems like single molecules and quantum dots have been studied. They have been studied extensively from the point of thermodynamics. The difference is that this requires to discuss fluctuations in greater detail. We will come to see how to avoid the discussion of fluctuations. When two disparate approaches to physical problems face off, as in the above case, surprises are to be expected. It has happened several times in physics, and there is no exception here. Classical thermodynamics engines like Otto engine study and use for over a century convert thermal energy to work. On the other hand, quantum thermodynamic engine affords us an opportunity to harness non-classical, non-thermal sources of energy arising out of quantum statistics to do mechanical work. This is one of the cases where you don't need thermal processing to get mechanical work. So I will do a simple back of the envelope calculation that reveals this. Consider harmonically trapped quantum Bose gas of n particles at 0 temperature. They are in a simple harmonic oscillator. So the total energy of the Bose gas will be h cross omega by 2 times n, because all the particles can occupy the ground state. But if it obeyed Fermi-Dirac statistics, this cannot happen. And Fermi-Dirac, the energy of the Fermi-Dirac is given by the expression. You have to put one particle in each level. We are not assuming any internal degrees of freedom for the fermion. Actually, you can take that. That will not make any difference. So E Fermi is given by this, and the Fermi are occupied. These are the levels occupied, and we get this. So now you see the difference between the two is fermion has higher energy, so ultimately the difference is so much. Now, this can be extracted provided we can change the system from fermion to boson. This is the basic idea. And some experiments which were reported in Nature actually triggered our thinking. And we proceeded to look at some simpler systems. The energy is non-classical and purely quantum mechanical origin, derived as it is from quantum statistical population distributions, functions of different particles. The main idea of quantum thermodynamics are to identify the non-classical equivalent of thermodynamic concepts, internal energy, heat, and work in a quantum system. Let ρ be a density operator that describes a quantum mechanical system coupled with thermal environment. H lambda be the Hamiltonian for the system. Lambda is a control parameter. And the internal energy is defined as average of H, which is trace of rho H. Where in the weak coupling element, rho is in the equilibrium state, we will take it to be the Gibbs state, given by the standard Boltzmann formula, which is rho equal to e to the minus beta h divided by h, where h is the partition function. We all teach this in statistical mechanics all the time. And k beta is nothing but 1 by kbt, and kb is the Boltzmann constant. Again, the Gibbs state entropy is given by minus kb trace rho log rho. Can I go to the next slide, sir?
By all means, Professor Mani, please.
Okay. The change in internal energy can be partitioned into two pieces. dE, d rho h plus rho dh. Now, I will argue that the first term is the change in energy and the second term is the change in the work done. Let us see why. Because notice that entropy changes when rho changes. So if entropy changes, d rho, the first term changes, and dq is related to TdS. So this is what happens here. That's the first term, indicating neither of these. Okay, the first, and then I have put something at the top. We all know what that is. That is path dependent. This is not a state function. And like we do this for work. Now let's look at the next term. The parameter h is varied. So let us think of a particle in a box. Particle in a box has energy h cross squared pi squared by 2 ml squared. Now, if I change L, the parameter of the Hamiltonian changes and work is done. Because I'm changing the length of the system is doing work, or somebody is doing work on the system. So that represents the work done. So this is the first thing which when you do quantum thermodynamics, we do. We associate with trace rho dh with dq and rho dh with dw. I will again wait for a small time and let me know whether this is okay.
Professor Mani, the slide reads well. Please proceed.
Pardon? Can I go to the next slide?
Yeah, sure.
Okay. Now it is straightforward to define quantum analysis of isothermal, isobaric, isochoric, and adiabatic process. There are some subtle points. We'll come to that. Hence, the various quantum analogues of the classical thermodynamics engine. The Otto engine, for example, consists of 4 strokes, 2 adiabatics and 2 isochores. By definition, adiabatic is one in which no heat transfer takes place between the system and the environment. It corresponds to a change in energy eigenvalues while keeping the populations, hence the von Neumann entropy unchanged. This is a very important point, which is there in thermodynamics of small systems. In isochoric system, where the volume is cell camps, the energy levels are fixed. The changes are in the population because in an isochoric process, the temperature can change. When the temperature changes, the Boltzmann function changes. If it is at a higher temperature, higher levels gets populated and so on. So the energy changes. Now, can I go to the next slide or shall I wait?
Please go to the next slide.
Okay. we conclude this brief survey of quantum thermodynamics, and we want to mention a few subtle points in which the classical and quantum mechanics differ. Now, let us look at a classical adiabatic process. This is something which is not a very easy concept to explain when we teach statistical mechanics. Consider a characterized by thermal, of which no heat is exchanged. That is an adiabatic process. When I make a small change on the system, how can I say the system has come to equilibrium? That is not obvious. And this is, if I'm not interacting with the surroundings, somehow the system on its own, it's a very famous problem. And I do not know any detailed mathematics of it, but there is a time scale. The time scale is in which the system comes to an equilibrium. And this time scale of coming to equilibrium should be less than the other time scale of when it is expanding. Thus, the time scale of the adiabat should be less than the decoherence time scale. Can I go to the next? Because this is a very important point.
Yes, please. Kindly go to the next slide.
Okay. Unlike classical thermodynamics, we have systems which are reversible and are in instantaneous equilibrium throughout. In quantum thermodynamic engine, we have the following problem. We all know quantum adiabatic theorem. In quantum adiabatic theorem, the system should move so slowly that if you want it to remain in the same level, the time scale should be such that it should be more than the time scale associated with the energy difference in the various levels. Of course, H cross is involved in making it unit. This is one of the important points in understanding. So a system may be an adiabatic classically, but it need not be an adiabatic quantum mechanically. Because when I am making the system move slowly, but fast compared to the energy level difference, the system will automatically, quantum system will automatically not satisfy the quantum adiabatic theorem. Okay. Now I will go to quantum Otto engine based on qubits. Three-level systems, harmonic oscillator, statistical ions have been extensively studied. In this paper, we study the quantum Otto engine with a working medium with a very small number of one-dimensional anions. We will talk about what is anions. Anyons, particles which are intrinsically have quantum statistics, which can smoothly interpolate between the bosonic and fermionic statistics. This has been going on for quite some time. It came from statistical mechanics, where fractionally quantum Hall effects were observed when anyons were discovered. I think Jain was an important contributor to this. Now, how do we do this? How do we change the statistics from fermion to boson and vice versa? Here is the main idea. I have some kind of a flux tube. B is a flux tube. And I have a charged particle which is going around. If I change when a particle goes around, it picks up a phase of e to the power of I loop of the integral A dot dl. A dot dl is nothing but the magnetic flux passing through this surface. I will repeat it. I have a magnetic field confined to this in this direction. When the magnetic field is in this direction, I have a charged particle which is moving in a ring. It is constrained to move in a ring. Now, if when it comes back here, if it were a boson, it should have the same phase. If it were a fermion, it should have the opposite phase. But in general, it will have some arbitrary phase depending upon the flux that is passing through this. So now I have a control of how to change the statistic from boson to fermions. Here it is. Magnetic flux is B into A. A is the area of the loop here, because we assume there are no magnetic flux here. Since this is infinitely long, the magnetic field will go out to infinity. Although it doesn't make sense about statistics of individual particles, it may be considered as a toy model of an anion. Again, this is a question which was raised right in the beginning when quantum thermodynamics of small systems were formed. The answer to it was, you give several Gibbs examples, and work with averages from the Gibbs ensemble rather than the other ensemble with a large number of particles. So that was the answer for that question. So let me repeat here. Although it doesn't make sense to talk about statistical injury, this may be considered as a toy model of an anion on a ring. To verify this, all we have to do is consider two particles on a ring and exchange their positions. The vector potential has only A5 by 2 pi r. The Hamiltonian for a charged particle, we all know that 1 by 2 pi m. This is just the standard gauge transformation we make and write it down, which is equal to, I write P phi as its cross squared so much. The normalized energy levels are given by this. N is an integer with eigenvalues. So now notice this Z. And E is nothing but where alpha is the value coming from given by the flux. This is a standard thing which we also use in superconductivity and so on. I will now go to the next slide. Okay, here is the diagram. I have entropy and the temperature. These two are adiabatic, entropy is constant. And these are isomagnetic. Instead of isochoric, we have written it as isomagnetic. Magnetic field is constant. The four strokes constitute are, the first step, we move from A to B. The system changes its temperature from T1 to TH. This is achieved by bringing it to contact with an infinite baths, several baths at each infinite temperature, T1 to T2 plus so on, and go on till it comes to TH. This is a standard procedure. You make infinite bath transformation to reach there, so that we can consider that in thermal equilibrium in the entire process, and we can apply the equations of thermodynamics. N dt is number of steps, and we get a reversal pass. This is because the entropy change in the reservoir and the system is zero at this stage. Similar argument holds from C to D. So I go from here to here, here to here. A to B and C to D are isomagnetic process. So thus called because no work is done along these paths. Recall that changes in energy levels are affected by changes in magnetic field. The strength of the magnetic field A to B chosen to be BH corresponds to the energy. EHN is given by this expression, where alpha H is equal to BA squared BH. Similarly, from C to D, the energy levels are here to here. Let me just tell you, the first one was the energy level change from A to B, and the second one was from C to D. Now it is very easy to calculate. Alternatively, we can keep the magnetic field constant and the radius of the ring. If I change the radius of the ring, it will automatically change. This is another way of doing the same thing. So we have two different methods. The experimenters can choose whichever is convenient to them. Now notice, if the radius A2 is greater than A1, the energy level decreases. Since the occupation probabilities remain the same in an adiabatic process, work is done as we go to the system as we go. So if I increase the size of the ring, there is more work done. Where I decrease it, the work done is the opposite. Note that only state B and D are in thermal equilibrium. B and D are in thermal equilibrium. These two states are not in thermal equilibrium. The efficiency of the quantum Otto engine is given by WQOT is equal to this 1 minus, you can calculate that expression clearly, which is, I substitute various values for PA and PB. Notice these B and C are equal because they are isentropic. Same way, these are entropic. So I can write it in this form. And one can simplify this, and I will not spend some time to do that. The sums appearing that can be calculated in a straightforward manner and can be given an analytic expression in terms of some things which I These are gamma functions of some general functions which I will not describe here, but they are all doable. There is no major problem. Jacobi theta function in terms of these. There are several other things which one can do to convert bosons to fermions. We have written one more in the paper, one more paper, we are about to write it, and that's where it is. And I thank all of you for the attention and the patience. And so if you people have any questions, I'll be more than happy to try to answer. Not that I know everything associated with this field, but I enjoy working in this area. Thank you.
Thank you, sir. We have about 10 minutes. We have enough time for interaction, feedback, as well as any comment. Thank you. I open to the audience.
Sir, can you please more elaborate about the anyonic word?
Yes. You see, in bosons, when I have not drawn the diagram, you can do that. But bosons, if I interchange two particles, the sign of the wave function doesn't change. But with fermions, it changes sign. If I do the same thing here, let me go to the diagram. Here, supposing I keep one more particle here, then I interchange. What does that interchange mean? This goes here and that comes from there to here. So the total change is essentially e to the power of I, the flux passing through this. Please realize this is one goes here, the other comes here. So the entire change is the full circle. So, but e to the power I a dot phi need not be equal to 0 or 5. Need not be an integral multiple of 2 pi or an integral multiple of pi. So that is why when I interchange these two particles, they don't have a property of fermion or boson. I hope I have clarified it. It's not. If not, I will repeat it in a slightly different way.
Yeah, thank you, sir. Thank you.
Fine. Yes, Haridas.
First question, why Otto cycle? There are many cycles in thermodynamics. Why did you pick the Otto engine?
Very good question, Haridas. With Carnot engine, it will not work very well because Carnot engine is independent of the system, as you pointed out in your book very clearly. And secondly, we can use diesel engine. The calculations are more messy.
Second question, you identify the d rho term with d bar q, but d rho is an exact differential. D bar q is not. So
Which slide are you talking about?
In your very first identification of the first law for the quantum case.
That is so only if it is a reversible process.
Whether it is reversible or not, d rho is an exact differential.
Oh, d rho, of course, is exact. That's correct.
But you identified with d bar q, which is not an exact differential.
That is correct. That is a exact differential when the system is in equilibrium. It is TdS.
Okay. Thank you.
Oh, you're welcome. We spent a lot of time trying to look at other engines, and ultimately we decided. Now, I want to make one remark about Haridas's book. That's the first place I learned that Carnot did not use the theory of heat that we use today. He had used some other liquid theory and so on, yet got to the result.
So is there any more question? Otherwise, we have saved 5 minutes. We can pass to the other speaker so that he may gain 5 minutes more.
Can I stop sharing?
Yeah.